Good morning, everybody. Welcome to the Catalyst webinar on how Catalyst can help the AEC community doing flow simulation. My name is Al Griffa, and I will be one of the two presenters today. So for today's webinar, we will go over an overview of our company, Catalyst, and why performing CFD is important for architects and civil engineers. We will then cover a couple of war stories, and this session will be done by Riccardo Rossi, followed by a live demonstration of the Catalyst CFD software. And we will end up with the webinar with a recap session and a few minutes for questions. Let me spend a few words about the presenters. Again, my name is Al Griffa, and I've been involved in software sales for more than 18 years. With companies such as Technomatics and Geomagic, providing software solutions in the area of CAE, computer-aided engineering, from process simulation to reverse engineering. Riccardo Rossi is a research associate at the University of Bologna in Italy and a visiting scholar at Stanford University in California. He holds an MSc and a PhD in mechanical engineering. He has 10 years of experience in CFD simulation of turbulence and industrial flows. He has published more than 40 papers in CFD and has also served as a scientific advisor in applied research projects in collaboration with leading companies such as Ferrari and Ducati. Before starting, some housekeeping. All participants are on mute, meaning that your voice cannot be heard. However, you can submit questions to the presenters. If you want to submit a question, just please use the panel on your right side and type in the question. We will try to address all the questions during the webinar and along our presentation and demo. But remember, there's also at the end, we are going to have a Q&A session as well. Let me spend a few words about our company, Catalyst. Catalyst was born as a spin-off of an Italian research center called CRS4, based in the beautiful island of Sardinia in the Mediterranean Sea. The founder, Marco Mulas, led the Fluid Dynamics group for 20 years, developing and using the very same core technology that you will experience today as a part of research and consultancy. So, although new and young, the code has been used for a number of years in various projects with code that has already been validated and proved. The company is entirely private with private investors. The headquarters are located in Italy with sales offices in Milan, in London, and for the North America, the headquarters is in North Carolina, and precisely in Cary, North Carolina. As we speak, about 1,000 people have downloaded our 2D free version. And also we have strategic partners in various areas like industrial, university, and research centers. Okay, so computational fluid dynamics, also known as a CFD, as the most sophisticated airflow modeling method, can simultaneously predict airflow, heat transfer, and contaminant transportation in and around buildings. So CFD provides answer to different questions. Let me throw out a few of them. Number one is, what sort of temperature distribution could I expect in an atrium under clear sky and summer conditions? Maybe another question can be, will the arrangement of supply diffusers provide adequate air movement? Or is the location of the radiators going to provide good comfort conditions? Maybe are there any region of stale air inside the buildings? So those are a few of the questions that CFD answers to, okay? And let's analyze some few of the advantages of doing CFD. Number one, we lower the construction cost by leveraging simulation rather than physical mock-ups or prototypes. There are money savings because we avoid physical wind tunnel tests and field measurement. Another way to look at it, we can be faster time to market because you have prediction capabilities performed virtually. You can have more energy efficient buildings. You can be more comfortable, you can create more comfortable living environment. So those are the few values that doing CFD can bring you. Let's review now a few more stories with some practical cases from the field, presented and discussed by an expert in the field, like Ricardo Rossi. Ricardo, please join me.
Thank you, Alberto, and good afternoon, everybody. So today I would like to show you some examples where CFD can be used to improve the design of buildings and also the design of the built environment in general. And I would like to start with some results about the simulation of the wind field and dispersion in Oklahoma City. So for those of you who are familiar with the OKC, you will probably recognize the Chesapeake Energy Stadium in the foreground of this picture here to the left. And then in this urban area, we also have some high-rise buildings in the background here that you can see in the city center. So to perform this kind of simulation, we need to create the geometry model first, and this is done here starting from GIS data, where GIS stands for Geographic Information System. And then from the STL, we need to create a computational grid, which in this case will look a little bit complex because of the complexity in this geometry. I'm not going to go too much into the details for the grid generation, but Alberto in a few minutes will show you how easy and fast is this task in Catalyst. So for today, I would like to go directly into the discussion of results for this type of flow computation. So here I'm showing some results about the wind field in downtown Oklahoma City. So in the picture on the left, I'm showing the wind speed in a horizontal plane crossing the computational domain. The wind is blowing from the lower left here in the picture to the upper right. And you can see how the buildings are interacting with the wind field. So we can see some wakes developing downstream of the buildings, not only in the downtown area, but also from the low-rise buildings like this one in the right side of the picture. And we can also see how different the wakes are when we compare these regions here to the side of the downtown area, where the velocity defect is not as high as in the case of the city center here. Of course, when buildings interact with the wind, there is also a lot of turbulence generation, as Alberto will show you afterwards in a simpler environment. So here in this picture on the right, I'm showing turbulence intensity, and red colors would show you the regions of the high turbulence intensity. And it is kind of interesting to see that the wake from the low-rise buildings, they generate much more turbulence than in the massively separated region downstream of the city center. So this is just to show you how much complex the wind flow can be when you have to deal with a real urban area like in Oklahoma City. So in these other two slides, I would like to also discuss a little bit about the effect of the complexity on the wind field on the transport of particles in the turbulent flow, like pollutants, for example. So of course, these results from that I've been showing to you before, they're really useful for issues like pedestrian comfort and loadings on buildings, but the transport process is also very interesting if you are concerned about the air quality in your construction area. So let me show you a short movie here where we have two different computations where the wind field, the background wind field is the same, but we are displacing the source location from the downtown area here to a point which is a little bit, which is located a little bit farther downstream in the from the city center. So keep in mind that the wind is exactly the same in the two cases, and in particular we are dealing with this scenario here where we have a very strong separation once again downstream of the city center. And this is the reason why it's kind of counterintuitive, perhaps in the very first minute that you look at this movie, where you see that the pollutants are moving basically upstream, so they're not following the main direction of the flow. So once again, this is another example to show you how much this kind of flow field and the transport phenomena can be made more complex by the interaction of the wind field with turbulence. The last thing I would like to discuss is also the effect of the wind angle, and to do this I'm showing some results for slightly simplified urban geometry. So now I'm not taking into account for all the details. I'm using this geometry of a bunch of cubes with different heights and a staggered arrangement, and I'm going to show you what happens if you have a wind angle which is maybe aligned with the cubes in this way, or perhaps in the other direction. So once again, we have a source here for sort of pollutant generation, which is located here next to the tallest building in the domain, and we're going to take a look at the dispersion process downstream of the source. So here's the first movie. We are looking at the concentration of pollutants from the top. So each of these gray square spots will be one of the buildings. So I'm running the movie now, and you can see the dispersion of the pollutants downstream of the source. Once again, you can see in the very first moment of the dispersion process that the pollutants are moving upstream first and then moving downstream. And in this direction, so the wind is coming from left to right, you see that the buildings are arranged in a staggered fashion, and because of this there is a lot of diffusion of the pollutants in the span-wise direction. So there is a very strong spread of the pollutant plume, basically. So now let's take a look at the other case. Now the wind is coming from the bottom and moving to the top of the image. Once again, we are looking from the top to the contour map of the pollutant concentration. Here is the source, and you can see that at the very beginning the pollutants are moving downstream. Only after a few seconds you can see that there is also in this case some upstream movement of the pollutants. And the interesting thing here to note is that there is a very different spread in the span-wise direction, because now the buildings are aligned. There are these channels basically created by the in this direction of the flow, and because of that there is much less spreading of the pollutants in the span-wise direction. So again, this is just to show you another result that should bring to your attention how much you can gain out of a CFD simulation. So for now, I'll stop here, and I'll go back to Alberto, that's going to show you a little bit of a demo from, with Catalyst from this kind of application.
Thank you, Ricardo. That's a great story about Oklahoma City. So before going to the live demo, let me give you at least a couple of reasons why you want to use Catalyst CFD to perform this type of analysis. Well, the first reason is Catalyst CFD definitely eliminates the meshing stage, saving up to 99% of the user preparation time. This is due to a technology that we have that is based on the immersed boundary method, something that we are not going into during this webinar. The second reason is that Catalyst CFD does not require any in-depth CFD knowledge because the use of customer-specific apps. Today I will show you the app just developed for architects, specifically for you, architects and civil engineers, to support your specific design flow and the and validation. So before going to the live demo, allow me another another slide just to anticipate what you're going to see in the easy workflow for Catalyst, summarizing 3 main logical steps. And the 3 steps are, number 1, you're going to import the geometry from a CAD system such as AutoCAD or Vectorworks or Bentley or whatever you use. It can be a solid, can be a surface. You import it in an STL format. Step number 2, you're going to define simulation parameters, fluid, boundary conditions, making a use of the specific app designed for the architect. Step number 3, you just run the simulation. At the end of the simulation, results such as velocity, pressure, and temperature are available, to be analyzed, displayed, and documented through, visualizers. So, let's set up the demo. The scenario is the following. An architect has to evaluate the impact of wind around a few buildings and evaluate the pedestrian comfort in a plaza right here in front of all the buildings. And what we are going to do is that we are going to analyze and compare 2 scenarios with one building with a high profile and the other one with a lower profile, and see the effect of the 2. Okay, so now let me iconize the presentation and run Catalyst. This is how Catalyst is showing. Let me make it a little bigger. So the first step to do, well, we are going to create a what we call a new case. Let's call it case number 1. Okay. So the first thing is that we are going to say that, well, this is what we call environmental flow. That is a flow used by architects and civil engineering. We're going to import some surface. Remember, the first step is to import the CAD geometry. And here we are going to import the west side of the plaza. You can see here. I'm going to specify a few parameters for the grid generation. We're going to import the east part of it. Okay, I'm going to define the same. The third thing we're going to do is that we are going to import the high profile building that is going to be at the center of the 3. Here we go. Okay. Say OK. Define a few parameters for the grid, and so on. You can see here, this is where, that's how the 3 buildings are going to look alike. Okay. Okay, I lost my my window right here. Okay. Sorry about that. I lost my window. So the next step is to as you can see here. Let me take a step back. As you can see here, the box here shows the area of the simulation. Maybe what we want to do is very far from the building. We want to take a little smaller area. Like for instance, we're going to do let's put 200. Those are meters, by the way. Okay. As you can see here, that's what we are going to have, a smaller boundary where we are going to be interested in the area, right? Now, we saw before that there's a grid generation, so that's what we are going to do. We are going to start a generation of a grid that is going to be used by the software to perform the calculation. As you can see here, that the grid looks like this. Let me give you a little, okay, where we have refinement, close to the ground, much better refinement close to the buildings. And while we are far from the buildings, we can use a coarser grid. Okay. Obviously, this grid is in 3D, as you can see. The other thing we have to do is that we have to define some parameters like the wind direction, the wind velocity, and let's put a value there. It's 5 meters per second. Then we have to decide where is the wind direction. So let's put it as something like that, north-northeast. Okay, so those are the information that we need. Maybe what we're going to do is that we want to do a calculation at summer day, 300 Kelvin degrees, obviously. The other thing, the last thing we have to do is that we have to specify some information about the gas. The gas is going to be the air. Okay, it's going to be a turbulent flow, and that's pretty much it. Okay, really, the last thing we have to do is that we have to do is define how many iterations we want to have to do the full simulation. Obviously, we can go hundreds of those, but for the sake of the, just put 20. I think this is going to give us a good indication. So we save it, and then at this point, we start the So at this point, what we're going to do, well, let's look at the log file. We see here that the software is going to take in account the grid, is going to take in account the geometry, and is going to perform the calculation. And this is the log file that if you want to have a look at it, or you're going to do, you can monitor it. Let me jump to the end of it while we are while this is crunching, so this is going to be a little more interesting. So this is the outcome of the simulation. So you can see here, those are our buildings in full 3D. The buildings are colored, showing a color map of the pressure. Actually, it's the relative pressure, the pressure over the atmospheric pressure. This allows us to calculate the forces acting on the buildings. Another thing we can do is that we can also show what we call the particles of the wind. Okay, so let me show you the particles. So this is the, if you take a particle of the wind, this is a trajectory basically of the wind. And one thing we can do here is that we do it. Let me start an animation of it. Okay, so you see this is the effect of the wind. It's very easy for an architect to understand what's going on now with a very visual indication. Okay. I think why we might be interested here is to take a better look, and what we are interested, actually, we are interested to understand what happens when, for a man standing in front of the building. Okay, so what you are going to do is that you are going to have maybe a 6 feet. You're going to see the effects of the particle at 6 feet. Okay, and again, what we can do is that we can start the animation of it and start the effect of it. I hope this is very clear. It's very clear for an architect to understand what's happening at this point. Another thing we can do is we can understand the different velocities and speed. Let me show you right here. So this is the velocity. Can you see here the various velocities? And what you can do is actually you can interact with that. You can go in kind of a section dynamically the entire plaza and see where, you can gauge the effect of the wind on a person. Okay, so this is what you can do with the with our software with a full simulation. Okay, let's close it. And by the way, while we were talking, this is what happened. We start the simulation, we run 20 iterations, and that you can see here the clear profile of convergency of the simulation, and it's going down. And probably if you have 200, 300 iterations, you will see a better convergence of that. But it just takes time, so you need to get an extra cup of coffee. But as you see, it was very quick to run 20 simulations. So now what we want to do is that we want to evaluate the effect of taking a different geometry, as I said before, the same building, but with a lower profile, and see what are the effects of that. So let me open again our case, okay? And we are going to replace the tall building with something that has a lower profile. Okay, you see that? That's a lower profile. Okay, I'm going to put some the usual information for the grid. I'm going back to the application, and let me change this to. Oops. We define a smaller area for our simulation, and again, so this is going to be our new plaza. Okay, start again our grid generation using our immerse boundary method that is a unique as a proprietary methodology. Save it. Now we are ready to run it again. So I mean, those are the steps that an architect is going to do and perform to do any simulation. Okay, so while this case is running, as I've done before, let's start and take a peek or the comparison of the two scenarios or the two cases that we run. So what we are going to see here, we are going to see that on the left side we have the low profile building. On the right side we are going to see the high profile building. See a pattern here? You see the difference? On the right side, as we are expecting, we were expecting obviously more turbulence. As you can see here, this area where probably is not going to be very comfortable for people to stand there, while with a lower profile, we have a better smooth lines, so less turbulence. So this is a great indication for an architect to select what is the best scenario for building a plaza. Okay, and this is proven, and this is something that you have done virtually without any testing. So so far we use a very simple geometry here. Let me switch gear and show you a different case where basically here we have definitely more complicated geometry. This is a real geometry about a stadium. And the study here and the challenge for the architect was to determine if the players on the pitch here, this is a stadium to play soccer, or what in Europe they say the football, to be sure that every condition the winds are not going to affect the players on the pitch, so that basically the stadium is going to offer a kind of a repair, a shield to the wind, so that the players on the pitch are not going to be affected by the wind. So this is a more complicated geometry. Obviously, it's going to take a little more than 2 minutes to run this. But if we are talking about here, we're talking about minutes, okay, maybe a couple of hours to run a complete simulation of this, okay. So This is what I want to show you, and what I'm going to do at this point, I'm going to go back to Ricardo. Ricardo, please introduce us the next theme that we are going to talk about, that is internal flows.
Right. Thank you. Thank you again, Alberto. So in this second part of my presentation, I would like to talk a little bit about natural ventilation, probably a topic that could be a bit more interesting for an architect. So natural ventilation can be used to reduce the energy consumption from the heating and air conditioning usage for a building. And the basic idea here is to take advantage of the of the flow of air, the natural flow of air between the inside of the buildings and the surroundings. So once again, I don't want to go too much into the details of this. I just wanted to mention that you may have natural ventilation driven by the wind. So in this case, it's really important to take a look at what's happening outside the building in terms of the velocity field and the pressure or even turbulence. And this goes back to the first part of my presentation, where I've been showing you that you can gain that kind of information from CFD computation as well. The other type of natural ventilation in buildings is generally what we call the stack-driven ventilation. And so in this case, the flow is driven by temperature and density gradients between the inside and the outside. So natural ventilation, the idea of natural ventilation is actually not brand new. The idea goes back to 400 before Christ. I'm showing here some examples from the Middle East, where of course air conditioning has always been a problem. So the picture to the left is showing you some examples of stacks in buildings in Pakistan. Some of them, they're also self-orienting, so they would orient basically based on the wind direction. And then the picture on the right is showing you some of the kind of famous Bagdir. Bagdir is the Farsi for cooling tower. So you can see some examples here of this tower that are used to cool down the inside of the building. But for today, I would like to focus on a case study which is a little bit more recent. So the case study will be about the building, the Y2E2 building at Stanford, which is the base of the civil and environmental engineering at Stanford. And as a visiting scholar there, I've been involved in this project where we wanted to perform some analysis of the a process that is called night purge. So basically the idea is to use the cold air in the evening to cool down the building and get lower temperature inside the rooms and the morning after, so that you would save some energy out of it. So the target for that was pretty challenging. The design was I'm sorry. So the design was targeted to 50% energy reduction, 80% of the building lit by daylight, and to do that, the building has some sensors inside that are used to monitor the functioning of the building, and some energy modeling has been performed in with energy tools like eQuest and Energy Plus that perhaps some of you may be familiar with. Let me just spend a few words about how it works, so how this night purge process works. So let me go back to the picture here, and let's imagine that during daytime, the envelope of the building and the inside of the building, of course, is going to be warmed up by the solar radiation. And so if we take a look at the temperature inside the building during the day, of course, we can see the temperatures inside the rooms and the offices going up, reaching the maximum around 4 o'clock in the afternoon. And at the same time, if you look at the this blue, light blue line showing the outdoor temperature, of course, the temperature of the air outside the building is going up during the day, but then it's going to cool down as the sunset sets in. So the idea is to use this density difference between the outside and the inside because of the different temperature to drive the flow from the outside into the inside of the building and to get the building cooled down. So the picture on the left is showing you the pressure distribution inside the building by the red line, and the blue line is showing the pressure outside. So if we take a look at the first like 2 or 3 stories of the building, we can see that we have a favorable pressure gradient that if you would open a window, then the pressure gradient will drive the flow inside the building. And this is what's happening around 8 o'clock in the evening here. So you can see that at some point the windows at the first floor are opened, and then we have the temperature inside the building dropping down because of the mixing of the cold air from the outside with the warm air inside the building. Around midnight, we have a disable temperature setting in because we don't want to freeze people the morning after, and so we want to go back to a temperature level which is lower than the one that you would have without the night purge, but still more comfortable for the occupants. So how does CFD come into play into the design process of the building if you want to use natural ventilation for your new building? So here I'm showing basically the basic approaches that you can use in your design process. So on one side we have observation or measurements, if you like. So you can make a model and do some testing. You'll get very high accuracy in your results, but also they are really expensive and they take a lot of time to get your answer. On the other side of the graph, we have less execution time and also less accuracy if you base your design on empirical models like this one, where you try to make an approximate relation between the mass flow rate with the openings and perhaps the temperature gradient. And then we have CFD that of course can be used to learn more about parameters in these approximated models. And of course you can gain more insight into the process of the night pores or natural ventilation, if you like, in general. So with this very last slide, I just want to show you the process of the mixing inside the building as the night purge goes by. And so if we look at the first picture here to the left, after 25 seconds from the opening of this little slot, we can see this cold jet stream coming in. Red is the warm air inside the building at the end of the day. And so we can see the mixing going on and the filling up process of the building volume. So I've been mentioning these empirical models, and we also have some reduced order modeling that can be used to study the dynamic of the night purge process. Here I'm showing a couple of examples of these simplified models, like the well-mixed model and the immiscible model. And of course, they can be used to get very accurate representation of the process. We can see here that if we compare the heat flux coming out of the building during the night purge process, the CFD is the black line, we can see that we have a good agreement with one of the model in the first stage, and then we have the opposite trend here where the CFD is comparing well with the well-mixed model, meaning that you can't use the simplified approach for the whole thing. You have to switch from the first one to the second one, and perhaps you have to make some tuning of these simplified models if you want to get the right answer. And of course, in this case, CFD can be available too. All right, so I think for today I'm going to stop here. Thanks for your attention for now. I'm going to go back to Alberto with this demo, and I'll be happy to answer any questions you have in the Q&A session. Thank you.
Very fascinating, Ricardo. Thank you very much for these nice war stories. So now let me show you how to perform a study on internal ventilation for a building, following what Ricardo was saying. Let me iconize the application, and let's go back to our software Catalyst. So what I wanted to show you is a case where we are going to study different type of ventilation for a building, comparing different scenarios where various options are considered using various window locations and openings. So what we are going to do here, let's create a new case. For the case number 2, Great Fantasy. We're going to do that. We're going to select an app that is called Internal Flow, and we are going to select the geometry. The geometry in this case is pretty easy. I mean, but it just to give you the idea how to perform studies for internal ventilation. So we import it, and we are going to set some parameters for the grid. We're going to, another thing we are going to do is we are going to define pressure and velocity for the input and output. In this case, at least in the first case, we are going to assume that the wind is coming from this direction. Okay, what we say, the Y direction. It's coming in this direction. So what we are going to do is that we are going to specify the wind direction. Let's assume it is going to be 3 meters per second, and the temperature, let's assume 300. Let's say it again, hot sunny day. The other thing we can do is that we can define the pressure of the outlet is going to be just regular pressure, atmospheric pressure. Save it. The next thing we have to do is that we want to create our grid. Remember that the grid that we want to create. So here what we are going to do, we are going to create some grid spacing. Let's put that, and put 2 here, and let's create the grid that we are going to use for our calculation. We have a little different scenario as before. This is an internal case where you see basically the grid is going to be inside the building, not outside. So let me show you the grid that we have inside the building. Okay, and this is in the other direction. So this is from the top actually. Okay, this is the grid that we are going to use. See if I hide the building, that's what it's going to be. Remember fluid, well, we are going to use a full turbulent model. Here we're going to use some initial parameters of speed, temperature. That's pretty much it. That's all we need to do. Oh, I forgot to do that. I need to define the number of steps. Yeah. Again, let's start with a very quick example of 20, just for the sake of it. Save it, and I believe that's it. That's all we need to do. Again, I don't know how many seconds, but in a couple of minutes you can define all the parameters you want. We start the calculation, and the software again is going to perform exactly the same step. Take the geometry, take the boundary condition, crunch them, and start the actual simulation. As you can see, no further interaction is requested by the user. So while we are crunching some numbers here, let's see the output of this simulation. What I want to do is that I want to compare 4 different scenarios. Okay. And the 4 different scenarios are relative to different openings of the windows. It's 1 window, 2 windows, 3 windows, and 4 windows. So the objective of the study is to assure that we have a correct, ideal ventilation throughout the entire volume of the building. This one on the left side is the result of the case that I just said, where we have only one windows open for the entrance and one for the for the outlet. That's it. On the right side, top right, we are going to have two windows open, one here where my cursor is, and one is the usual at the end of the building. Bottom left, well, we have three windows open. You see also this window is open. In number 4, we have all the windows open. So here we have different scenarios that an architect can use to evaluate what is the best ventilation possible for a given building. Okay. And again, it's a very easy, very colorful, very intuitive way to perform a what-if scenario. Very useful for architects, because you don't have to build a prototype. That's everything is virtual. If you go back to our simulation, I think we are going to be close to our 20 simulations. You can see again the convergence is there. We just need a little few more seconds just to close the 20 iterations. So really, in a couple of minutes, you have the entire case solved. So those were the two demos that I wanted to show you how Calid can answer and kind of duplicate what war stories heard from Ricardo can be simulated with our software. So let me go back to our PowerPoint presentation just to summarize and conclude. Okay, so we saw this internal ventilation demo, and what I want to do is a recap what we have seen so far by starting to summarize the two major values offered by Calid CFD. The number one is Calid CFD streamlines and definitely shortens the time to perform a CFD simulation. Step number two, Calid CFD does not require any in-depth CFD knowledge because the use of customer-specific apps, such as the app that we saw and use today, developed specifically for you architects and civil engineers. You could see that it took me no time, no effort to input very simple and very intuitive parameters like speed and temperature, something that you are accustomed to do and to deal with. Okay. And again, remember the 3 steps that you needed to do and to perform. Number 1 is import a CAD, a geometry from AutoCAD, Vectorworks, or Bentley, or whatever other CAD that you use. Define some parameters and press the start button. Those are the 3 fundamental steps to perform the simulation. So, if you want to learn more about our revolutionary CFD software, what you can do? Well, number 1, you can always go to our website, www.calid.com. You can download technical papers, case studies, application description, and everything about our software. Number 2, contact our office. Contact me in my office in Cary, North Carolina. You can also send an email to sales@calid.com. You can also follow us on Twitter, Facebook, LinkedIn. We are there. Last thing is this webinar has been recorded, and so you can review it at any time. We are going to put it on our website later this week so that you can access, you can retrieve it, and you can play it. Maybe you want to show it to your partner, your colleague, your friends. Also, this is a series of webinars. We always do webinars, so please stay tuned for the next webinar. Okay, and we are going to show you, another war stories. We are going to talk about that. Now, let's open for questions and see what are the questions that you have. And okay, so one question that we have is a technical question. Technical question is Okay, let me see. Okay, do you support turbulence? Which kind of models of turbulence you support? Well, we support different type of turbulence, and you know, right now we are supporting 3 models. I don't know if you are technical, but one is it's called SNA, it's Polar-Maris, KG, and K omega. Those are the models that are more frequently used in our domain. The second one is, okay, well, that's easy. Which kind of operating system you're supporting? At the moment, we are supporting Windows. All this demonstration has been performed on Windows. And also we support Linux. So that's the answer. Do you have a demo version? Yes, we do have a demo version. There are 2 ways. One, we actually have a 2D version that right now is on the website that you can go and download. But also we offer a 3D version. If you are interested in seeing more about that 3D, just talk to me and we can sort it out. Next question is is going back to the operating system. So do you support Mac OS? Yeah, it's in our plan to support it. We don't support it as today, but definitely we are going to support it in the very near future. So we are coming out with definitely with a version for Mac OS. I know that architects and I mean your colleagues are really using a lot this Mac OS. And by the way, I'm also a big fan of Mac OS. The last question, let me take a last question and then I will conclude the seminar, is do you support scripting? Well, there are different types of scripting that we support. There are different levels. One thing is that, you know, you can write external macros to execute multiple jobs overnight. So let's say that you have those 5 cases, the 4 cases that I showed before, where you have 1 Windows, 2 Windows, and 3 and 4 Windows. What you can do, you can prepare your studies before leaving the office and then run them overnight, okay, at the same time. So that is something that definitely you can do. So given the time, I would wrap it up at this point. I want to thank you very much for your time. Looking forward to talking to you directly or by email. Again, thank you very much. Stay tuned for the next webinar. Thank you. Bye-bye.